Now let us try and calculate 99 square using a plus b whole square. How do we do it? Should we write it as 90 plus 9 whole square? Now we see that if we write it as 90 plus 9 whole square, we have to calculate 90 square and 9 square, which is not very simple. Is there any other way in which we can write it? Yes. 99 can also be written as 100 plus negative 1. So 100 plus negative 1 is 99, and then we can square it. So again I have something in the form of a plus b whole square with much simpler values. It is simpler to calculate the square of 100 and 1 as compared to calculating the square of 90 and 9. So we use these. Now 100 is my a, negative 1 is b. So a square is 100 square, 2ab is 2 into 100 into negative 1, and b square is negative 1 square. So 100 square is 1 and 4 zeros. 2 into 100 into negative 1 becomes minus 200. Negative 1 square is plus 1. So what do we get? We get 9, 8, 0, 1. So this is what we get. From 10,000, we subtract 200, we get 9,800, and then we add 1 to it. So this is 9801. So see how simple this huge calculation has become with the help of this identity. But notice that we have used negative 1 here in place of a positive value. So let us see what happens if we substitute a negative b in place of b in this identity. So if we substitute a negative b, we get a plus, and negative b becomes minus b. A minus b whole square is equal to a square remains a square plus 2a into negative b, it becomes negative 2ab, and negative b whole square. So negative sign is also squared, so it becomes b square. So a minus b square is a square minus 2ab plus b square. So this is another special identity. Let us verify it using expansion. We have a minus b whole square. We can write it as a minus b into a minus b. Again we use the distributive property. So we take this a multiplied with this expression, minus b multiplied with this expression. We multiply the terms. A multiplied with a gives us a square. A into negative b gives us negative ab. Negative b into a gives us negative ba. Negative b into negative b gives us plus b square. So these are like terms and we can combine them to form a square minus 2ab plus b square. So this is also a special identity. And whenever we have something in the form of a minus b whole square, we can directly use this identity. Now let us prove this identity also geometrically. We have a square of side A. We take a point here such that this length is b. We take a point here such that this length is also b, and we divide it in 4 parts. So this is what we have. Now this area is a square. This side is a minus b. This side is a minus b. this side is also A minus B. So this is the square of side A minus B, and hence its area is A minus B whole square. So this red area is A minus B whole square. This A minus B whole square is equal to the area of this large square, which is A square, minus these three areas. So it is A square minus the area of this part, minus the area of this part, and minus the area of this part. So we have A minus B whole square as A square. This entire area, which is A square, minus the area of this part. So what is the area of this part? This length is A and this is B. So this is a rectangle with sides A and B. So this is A square minus AB. And now let us subtract this area, which is the blue area. So this side is B and this side is A. So we subtract BA. Now we see that we have subtracted this region twice, once with this and once with this. So we have taken the entire area, subtracted this, then subtracted this. So we have subtracted this twice. We need to add it once in order to get this area. What is this area? This is area of a square with side B. So we add B square to it. So we have A square minus 2AB plus B square, because we have combined the like terms. Hence, A minus B whole square is equal to A square minus 2AB plus B square, and we have proved it geometrically as well.